Forget giant antennas. We are already broadcasting our presence to the cosmos in 5 accidental ways. The old radio leakage is fading, but our planet is giving itself away through chemical biosignatures in the atmosphere. Proof of life. Then there's the heat from our cities, the web of nighttime lights, and the flash of our orbiting satellite Glints. Which is the strongest beacon? There are 5 key ways scientists think aliens could discover Earth's presence, and most have nothing to do with big antennas. Our chemical atmosphere, our city lights, our heat signature, our radio leakage, and now, even our satellite Glints. Let's count down each one and ask, which is most likely to give us away? Our accidental beacons to the cosmos. If another civilization pointed a radio telescope at Earth, what would they actually detect? The short answer is, not much, but just enough to raise curiosity. For roughly a century, our planet has been radiating a constant background of weak radio and television signals into space. Scientists call this radio leakage. In plain terms, it means that whenever we transmit something by radio waves, whether for communication, radar, or broadcasting, a fraction of that energy escapes the atmosphere and keeps traveling at the speed of light. It spreads freely until it grows too faint to separate from natural cosmic noise. Every transmission begins strong but loses clarity as it moves outward. Within only a few light years, even the most powerful broadcast becomes almost impossible to tell apart from static. Astrophysicists describe this fade as an inverse square drop. The farther the wave travels, the weaker it becomes following that geometric rule. So, while a wartime radar pulse from the 1940s might have been measurable near the edge of the solar system back then, it would now be drowned by the Milky Way's background hum. Early radar systems sent out some of the strongest human-made radio bursts ever produced. They used concentrated pulses to locate aircraft or distant weather, but their beams fanned out widely. TV transmitters worked differently. They emitted steady carrier waves around the clock. Those signals carried the sound and images from early broadcasts, and some of that energy kept moving outward. Over time, these emissions filled a low-grade bubble of radio chatter about 100 light-years wide. Compared with the galaxy's diameter of roughly 100,000 light-years, it is a microscopic sphere on the cosmic scale. Within that bubble lie a few thousand nearby stars, but most remain well beyond the reach of even our noisiest transmissions. Researchers studying this thin shell of expanding noise note that the loudest signals came from the mid-20th century, before digital systems took over. Modern communication satellites and fiber networks are more efficient and leak far less radio power into space. Our planet is, paradoxically, becoming quieter as our technology improves. While the faint shadow of old broadcasts is still expanding, its front edge grows weaker each year relative to Earth's current output. Not all signals leaking away were accidental. Some were sent intentionally, but mainly for demonstration. In 1974, scientists sent the Arecibo message, a tightly focused radio pattern encoded with simple information about life on Earth, toward a star cluster 25,000 light-years away. The Voyager probes, launched a few years later, each carry a record imprinted with sounds and images chosen to represent Earth. Both gestures were symbolic. Physicists calculate that by the time the Arecibo transmission reaches even the nearest stars, it will be far below the detection threshold of today's largest radio telescopes. This contrast between romance and reality often surprises people. We like to think of ourselves as shouting across the void, but from an astrophysical view, our voice is more a whisper. For an extraterrestrial civilization to notice us, it would need equipment with sensitivity far beyond what we currently possess. giant arrays able to tease structured patterns from vast numbers of natural radio bursts. If extraterrestrial astronomers were truly scanning nearby space, the best clue they might pick up wouldn't be reruns of bygone TV shows. It would be the steady, artificial rhythm of planetary radar emissions used for mapping asteroids, or the narrow band frequencies emitted by communication satellites. These create consistent, repeating features unlike anything found in nature. Such patterns might hint that a technological culture once arose on a small, blue planet orbiting a sun-like star. So, if anyone is listening closely, they may already sense a faint trace of engineering from our direction. But radio isn't our only giveaway. Even if every transmitter fell silent, our world would still broadcast its presence in other ways, through the light, color, and warmth of an inhabited planet, the planet that gives itself away. Even if we went silent tomorrow, Earth's presence would still be revealed by its environment. Our world broadcasts information not through noise, but through the light it reflects and the gases it contains. That glow, subtle to us, would be striking to anyone looking from afar with the right instruments. Modern astronomy has shown that a planet's atmosphere can speak volumes about what lives or operates on its surface. Astronomers now use a method called spectroscopy to study distant planets. In plain terms, spectroscopy means splitting light into its component colors to see which wavelengths are absorbed. Every gas leaves a distinct pattern, like a barcode. When a planet passes in front of its star, some of the starlight filters through the atmosphere and carries those fingerprints with it. By examining which parts of the spectrum are missing, scientists can tell whether there is oxygen, carbon dioxide, or methane in the mix. The consensus view is that this technique provides strong, indirect evidence of what a planet's air is made of. From a long way off, Earth's atmosphere stands out for a special reason. It holds large amounts of oxygen along with smaller traces of methane. Those two chemicals react with each other quickly, meaning they cannot coexist for long without a constant source renewing them. On Earth, that source is life, mostly plants and microbes. If another civilization measured a similar imbalance in our air, it would serve as a biosignature, a chemical hint of biology. This idea has become central to NASA and the European Space Agency's approach to studying exoplanets, the planets orbiting other stars. Satellites in Earth orbit have already recorded our global spectrum. They show sharp lines of oxygen and water vapor with faint signatures of ozone and methane. Researchers use these data as a reference model for identifying life-friendly conditions elsewhere. Telescopes such as the James Webb Space Telescope have begun detecting similar molecular fingerprints in the atmospheres of nearby exoplanets. Future observatories, some still in design, may compare those readings directly to Earth's known profile. But gases are not our only giveaway. Artificial light traces another kind of signature. From orbit, city lights form a web that marks where people live and how energy used changes over time. Astronomers have simulated what Earth's night side would look like if viewed from several light years away. Even with today's technology, the brightness of entire continents would blend into faint glows, but patterns might still reveal organized activity. The upcoming Extremely Large Telescope, or ELT, along with next-generation space observatories, could in theory pick up comparable nighttime glows from alien cities if they exist. Thermal patterns add yet another layer. Earth emits infrared radiation, the kind of heat our skin can feel but our eyes can't see. Human activity alters that emission. Concrete and asphalt hold warmth longer than soil or forest, creating distinctive temperature differences that repeat every night. Mining, industrial zones, and urban centers also contribute excess heat. If observed from afar, these changes would make our planet's heat signature less uniform than that of a purely natural world. Scientists use similar measurements to study exoplanets and to infer whether their surfaces might be dynamic. A final clue comes from our growing collection of satellites and debris. Sunlight reflecting off metallic surfaces produces quick glints that move in predictable orbits. Over time, their combined brightness forms a flickering halo around the planet. Researchers modeling Earth's reflectivity note that this artificial glitter could be visible across great distances if monitored continuously. The pattern would differ clearly from the steady reflection of clouds or ice. Taken together, Earth's changing chemistry, light, and warmth all reveal intelligent activity. Even without sending a single message, our planet already announces that something unusual is unfolding here. And if these traces could reach unknown listeners, the more difficult question waits on our side: whether being discovered is something we truly want. Conclusion: Earth already speaks through light, chemistry, and motion, even when we intend silence. Anyone scanning from afar would see a signal written in our planet's atmosphere and changing glow. The search for other worlds now reflects that same awareness. Each observation we make is also a form of self-recognition, a reminder that to distant eyes, we could already be the anomaly. Upcoming observatories will bring this exchange closer to balance, allowing us to detect planets that reveal themselves as we do. In that future, hearing and being heard may become the same act across the quiet, shared sky.